Hey everybody, good afternoon. Welcome to Momentum. Let's crash some stuff. Let's start with impulse. An impulse is nothing more than a force that acts over a time. So like, let's say you're running along and you smash into the wall. You're only in contact with the wall for a certain amount of time for that force acts over. And typically when we have a collision type of interaction, there will be a beginning time and an ending time of the force. This area underneath the graph is the impulse. It's the force times time. And if you're in calculus, that's the integral. Now, for us that aren't in calculus in this class, then what we will generally do is we'll have a shape like this where we can take the average force over that time is our impulse. Now, what does an impulse do? Well, an impulse changes the momentum of an object. We'll talk more about that in just a second. A larger force over a shorter time can exert the same impulse. So say like right here, if we have a short time period, we'll have a higher spike force, or we can have a longer time period and a shorter spike force. And the area underneath these two curves can be exactly the same. So you get the exact same impulse, the exact same change in momentum. So like you can get on the highway and barely step on the gas and you'll eventually get up to interstate speeds. Or you can stomp on the gas, peel your tires, and get up to interstate speeds very quickly. So you get the same exact change in momentum, but over a longer or shorter period of time. This is why boxers wear gloves, by the way, because the gloves are cushy and they extend the time of the impact, thereby lowering the overall force that a boxer gets to their skull, and that actually reduces injuries so that they can fight longer or have a longer career. So here's some data from an experiment. What's the impulse in this particular one? So we have a kind of a weird impulse. It's flat here, about 4 newtons, and then it jumps down at 15 seconds down to -8 newtons. All right, so you just find the area. So I have a positive impulse here. It's 4 newtons times 15 seconds, or 60 newton seconds. And then down here, this section is -40 newton seconds. So you just take the positive and the negative, add them up, so the net impulse over the total time would be 20 newton seconds. Don't worry about the shape of the graph, whatever shape of the graph they give you on the test, just find the positive area and the negative area, sum them all up, and that's the total over that entire time period. So let's talk about momentum. So momentum is a vector. It's a vector mass in motion, m times v. The momentum has the same direction as the velocity. So if you're going that way, then you have momentum in that direction. If you're going up, then you have momentum in the up direction. So a bug and a bus can have the same momentum if they have the same m times v value. So this bug is flying to the left. It has a negative velocity, it has a negative momentum. It has a small mass but a high velocity. This bus has a large mass and a small velocity to the right. They can have the exact same magnitude of momentum, but one will be positive and one will be negative because they're in opposite direction. Impulse and momentum. So let's tie these two ideas together. An impulse changes the momentum of the object. So the impulse, that graph, force times time, will equal how much the momentum changes. Not how much the momentum is, not how much the momentum was, but how much the momentum changes. Momentum final minus momentum initial. So the change in momentum is in the direction of the force. All right, so here, a ball is thrown against a wall. So it has an mv originally going towards the wall, to the right. The wall pushes it, gives it an impulse to the left. So its impulse changes to the left. Okay, what is that change? Well, the initial momentum was mv. The final momentum was -mv. So please pay attention to that because that shows up on the test always every year. The change in momentum is final minus initial. Our final is negative minus our positive initial gives us a -2mv. So make sure you pay attention to the signs. All right, so here's a sample problem. We have a 0.15 kilogram ball traveling to the left at 20 meters per second, struck by a bat over a time period of 0.001 second. The ball reverses direction and travels off with a speed of 40 meters per second. Now, reverses direction. Dun, dun, dun. Fateful words that you have to pay attention to because remember, for momentum, it's a vector. The direction matters. So what is the change in momentum of the ball? What's the impulse from the bat on the ball, and what's the average force on the ball during this 0.001 second. All right, pause the video, see if you can solve that, and then I'll show you the answers. Our change in momentum is mv final minus mv initial. Since the mass of the ball is not changing, I just factored it out. Mass of the ball, I called to the right positive, the final velocity direction positive. And then that means the ball was traveling to the left in a negative direction. So minus the initial. Put that all together, you get 9 kilogram meters per second. So what's the impulse? Well, the impulse will equal that change in momentum. So since the change in momentum was positive to the right, then the impulse is the exact same to the right. And then if we divide by the time of 0.001 seconds, we get that the fact that the bat exerted a force on the ball on average of 9,000 newtons. Remember, a system is just a collection of stuff. It can be a single object, it can be a group of objects, it doesn't matter. You just decide for your solving of the problem what your system is. So a system is considered open if there's an external force on the system. So like if I take this, okay, and I drop it, okay, if I'm only talking about the antenna ball here, it's not a closed system because gravity's pulling on it. So gravity is pulling it down, so there's a force from the outside. So this ball that's falling down towards the ground, gravity is an outside force, so it's an open system. Then when it hits the ground exerts a force up on the ball, our system, and so it's also not a closed system. It's an open system. So how about this girl? If we just take the girl swinging back and forth. All right, well, there's outside forces on the girl. There's gravity down, there is a tension force up, and these forces don't cancel. So that's an open system. How about this car right here, this white car? Well, this white car is flying through the air, gravity's pulling it down, and this other car is exerting force back on it, so the white car is not a closed system. The momentum of open systems will change when there's an outside force. Now let's talk about closed systems. A closed system is one where the net force acting on the object is zero. That means all of the forces that are acting on that system would be internal. So like for instance, if we take this antenna ball again and we consider it and the Earth together, then the gravity force is internal. And then when it hits the ground and bounces, that force off the ground from the Earth is still internal because that's a force between it and the Earth. So the ball and Earth together would be a closed system. How about two planets? Here's two planets that are colliding, but they don't have to collide. Say like the Earth and the Moon and the Sun. If we include all of the ones that have significant gravitational force on each other, then all those forces are internal. So that is a closed system. Football players. Now, all of these people that are colliding, we have to include them all in our system because they're all exerting forces on each other. How about the ground and gravity? Well, if the gravity force up is equal to, if the normal force up is equal to the gravity force down, those forces cancel. So there's not a net force from gravity and the normal force. So we would not have to include the Earth as long as the Earth or gravity is not accelerating them because they're being canceled out. So if we include all these football players here together, then that would be a closed system. Same here of this tanker hitting another boat. There's a buoyancy force up and a gravity force down, but they cancel. And as long as there's not a lot of frictional drag from the water, then if we include both these boats, then those are the only two net forces that are acting on each other, and we make the internal, and so now it's a closed system. How about this car running into this tree? Well, okay, that would not be a closed system because this tree and this car are exerting forces on each other. All right, well, what if I include the tree and the car? Okay, well, now I've included the tree and the car, but the tree is attached to the Earth. So I'd have to include the Earth because the Earth is exerting forces on the tree, and the tree is not free to move, okay? So I'd have to include car, tree, Earth, All right, and that would be hard for us to consider because it's hard for us to consider the Earth in a collision. All right, how about this cat? This cat is falling down on this skateboard that's going to the right. Now, there's obviously forces up and down on the cat and the skateboard that aren't completely canceling because the cat is falling, so it's accelerating down, and then when the cat hits the skateboard, the cat accelerates up so that the cat stops. So in the vertical direction, we do not have a closed system. But in the horizontal direction, we do have a closed system because as long as there's not too much friction, then between the skateboard and the Earth, all those forces in the x direction should cancel out. Why is that all important? Because if the forces are all internal, then what we end up with is conservation of momentum. The momentum of the system doesn't change. So for this car, we can't use conservation of momentum. For this cat and skateboard, we can use conservation of momentum in the x direction, but not the y direction. A system that has no net internal forces, you'll have conservation of momentum. So let me show you. A pool ball comes along here, hits the 8 ball. I need to include them both. Now, the pool ball has gravity on it and a normal force up, but they cancel. So I don't have to worry about including the Earth. So if I include the pool ball or the cue ball and the 8 ball, then when they hit each other, they exert equal and opposite impulses on each other, Newton's third law, right? And those two will produce equal and opposite momentum changes. But the key thing is they're exactly equal and they're exactly opposite. So the momentum of the 8 ball changes? Yes. Momentum of the cue ball changes? Yes. The momentum of the system that includes them both, does that change? The answer is no. Momentum remains the same. So we can have what we call conservation momentum. And remember, conservation in physics just means that it stays the same. All right, so the momentum of the system stays the same. All we have to do is take mv for the first object and mv for the second object. Initially, add them up. Remember, they're vectors. So this direction, one will have to be negative. And then we take that for them at the end, mv, final, and this must be true. If we have 3 objects, we'd have 3 mv's at the beginning and at the end. So now conservation of momentum. Momentum is always conserved in a closed system. However, kinetic energy of the system can change because in a collision, if the forces are of certain kinds, then kinetic energy will be converted into thermal energy or heat, all right, or sound. Eventually turns all into heat anyway. So we have 3 distinct types of collisions. You remember, in every one of them, momentum is conserved. So we have first an explosion. In an explosion, momentum is conserved. However, the kinetic energy at the end is greater than the kinetic energy we start with. So like for instance, we have these 2 skaters over here. They begin at rest with no kinetic energy and no momentum. And then they push off each other and fly apart. And when they do, the final momentum is 0. The initial momentum was 0. But the kinetic energy at the end is now something, and it was 0. So the kinetic energy's gone up. So other types of energy have been turned into kinetic. Another example would be a gun firing. The bullet goes forward, the gun goes backwards, so the recoil. Where did that kinetic energy come from? Well, it came from the chemical energy that was in the bullet. In an elastic collision, I like to call it the perfect bounce. This is when an object or the objects of the system don't lose any kinetic energy. Momentum is conserved and kinetic energy is conserved. This occurs when in the atomic world all the time. So like the air molecules in this room are all colliding around, and when they collide with each other, they don't lose any kinetic energy. So they don't slow down overall. If they did, they would all slow down and eventually stop, which would be absolute 0, by the way. And then gravity would all pull them to the floor, and we'd all suffocate in an absolute 0 freezing room. So that doesn't happen. So we know that these collisions have to be elastic. If we would have an elastic collision, say like with this ball right here, and I dropped it, it would bounce back to the same height forever. Okay, so we don't see really perfect bounces or elastic collisions very often in the real world. We get things pretty close, like those carts in class that had the magnets that bounced off each other. That was very close to elastic. But Still little heat was generated. Most things we see in the real world are not elastic, they're inelastic, and so some of the kinetic energy gets turned into heat. So a ball bouncing off the floor doesn't actually bounce to the same height, it bounces lower and lower every time, like you see here, and heat is generated. There's a special case of this bad bounce, and that is the worst bounce possible, when they hit and stick. So like these two would come along and they would go towards each other and hit and just stick together. Okay? Anytime we see that, we know that it's an inelastic collision. Anytime we see a bounce, there's no way for us to know unless they tell us in the problem, or we calculate the kinetic energy before and after to compare to see what it was. An example of an inelastic collision would be a person running and jumping onto a boat, runs and jumps onto a boat, and then they go off together. They're now stuck together, one object. Or like a football tackle, a good football tackle where the linebacker collides with them, ties them up, and they both fall over together. Okay? So they hit and stick. A stationary 1,000 kilogram cannon fires a 90 kilogram clown at a speed of 75 meters per second, as seen in the figure below. So here's the before picture, here's the after picture. What's the recoil speed of the cannon? All right, so this is an explosion. So we have momentum initial equals momentum final. So we have mv for the clown, and for the cannon before and after. But beforehand, nothing's moving, so it's 0. And then afterwards, we have cannon and clown. And I have the clown going with a positive velocity. So when we solve this, we get a negative velocity for the cannon, because the positive momentum of the clown must equal the negative momentum of the cannon, so it adds up to the original 0. So we started with no kinetic. We ended up with kinetic motion afterwards. Remember, kinetic energy is 0 or positive. It's never negative, because it's a scalar. So this is an explosion. Here's another example. We got two train cars colliding, as shown in the figure. What's the final speed of the one on the right? So this one on the left was stationary. This one was zipping along, hits it, and then the one on the left takes off, and this one must slow down. So mv equals, momentum before equals momentum afterwards. So we have mv for the car on the left and the right, before and after. Initially, the car on the left was 0. Plug in our numbers. I chose to the left to be positive just to make the math simple, and I get a final velocity of this car to be 5 meters per second. Now, the math here is not shown, but if I calculate the kinetic energy of these two before, 1/2 mv squared for both, I get this. And afterwards, if I do the same thing, 1/2 mv squared for each one, add them together, I get this. So the final kinetic energy is less than the initial. So this was an inelastic bouncing collision. So not all bouncing collisions are elastic. All right, let's talk a little bit about center of mass. In a closed system, remember there's no net external forces. We've defined it to include all the objects that are interacting, and they're all free to move, so there's no other outside forces hindering their motion. Right? So there's no net external forces. Whenever this occurs, then look, the sum of the forces on the system are 0. So that means that the acceleration of the system as a whole must be 0. So that means an object at rest stays at rest, and an object in motion stays in straight line, constant speed, constant velocity motion, right? So that's true for a system. So like here's an asteroid that blows up. If it was sitting still before, even though all of its parts fly apart, if I include the asteroid as my system, then afterwards all the parts fly away, but the center of mass of the system, because there were no external forces, stays at rest, stays right here. And then in our picture from earlier, we had those two railroad cars, and one was moving to the left and the other one was stationary. And so the center of mass was closer to this one because it's twice as heavy. And as we move to the left, this center of mass will move to the left. But after the collision, the center of mass of this system, it never changes its motion. It keeps the same velocity. So I'm going to show you a little simulation of that real quick. Here's a real simple momentum simulator. So the green arrows represent the velocities of the balls and they're colliding off each other. Now I have it set for elastic. I want you to notice the kinetic energy. When they hit, the kinetic energy remains the same. If I make this inelastic, then they still bounce off each other, but notice their velocities are less afterwards and they've lost kinetic energy. If I make it totally and completely 100% inelastic, then they'll hit and they'll stick together, and we've lost the most or the maximum amount of kinetic energy while still maintaining conservation of momentum. Momentum is conserved in each one of these collisions. And the only way we can tell in a bouncing collision, say like this one, whether it is elastic or inelastic is to look at the kinetic energy before and after. I'm going to take it back here, and this time I'm going to get rid of the velocity vectors and just show you the center of mass. This X is the center of mass. Watch its motion. Notice how the center of mass's motion never changed during the collision, and it won't matter what kind of collision I make it. The center of mass X continues to go to the right the same as it was at the very beginning. All right, let's look at a more advanced picture. Here are two that are colliding in 2 dimensions. Now we don't have any 2-dimension problems on our test, but just to show you, watch the center of mass. Notice its motion never ever changed in that collision. Here's another simulator from O Physics. If you want to go there, you can look at it yourself. And if I hit run, I have a big block here moving to the right at 10 meters per second, the blue block moving to the left at 8 meters per second. Here is the center of mass, COM, center of mass. And when they collide, lots of things change, but that center of mass motion doesn't change at all. So the velocities change direction. The red one was going to the left, sorry, to the right, now it's going to the left. The blue one was going to the left, now it's going to the right. The momentum swap around, but the velocity of the center of mass never changed, and the momentum of the system never ever changed. Here is another one from O Physics. This is an explosion type of collision, and I have a red box and a blue box. You can barely see it probably in your video. There's the center of mass location right here. Now they're going to move to the right and then they'll explode apart. Watch the center of mass. Center of mass continues to move off in the same direction it was going before. The velocity of the system is right here, and then they explode apart, both of them still going to the right. If we plotted the velocity of the center of mass, it would continue to just go straight forward because the momentum of the system and the motion of the center of mass never changes as long as you have a closed system with all of the objects that are interacting in this. So as we saw in our simulation, if the center of mass is at rest, like here is a person on a boat, the person walks to the left and the boat will move to the right, so that person has moved left, boat has moved right, center of mass stays in the same place. Or if we have 2 astronauts out in space and they have a rope between them, if they pull in on the rope, doesn't matter who pulls in on the rope, the center of mass is here between them and they will both move towards the center of mass. If we have objects that are moving already, then the center of mass continues to move after they separate or collide or whatever happens. Here are 2 people on skates, a adult and a child, and they're moving to the right with a common center of mass moving to the right. And then after they push off of each other, the child is moving faster to the right, the adult is moving slower to the right. Center of mass continues to go forward in the same direction, never changing. All right, that's it. That's conservation of momentum. That's the basics. Our next video, we're going to work some practice problems. See you then.